Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the previous session, we discussed a transfer matrix method for solving torsional vibration problem, which we know is called Holzer's method, wherein the transfer matrices are used to generate an overall transfer matrix representing the entire continuum, and then applying boundary conditions we can develop or find the frequency equation, which is iteratively solved. We discussed how the root searching method helps us locate the eigenvalue or the natural frequency, and that is the way we solved it for torsional vibrations. We now extend that method to understand how similar transfer matrix is formulated for investigating the lateral vibrations of a typical system, and in that context the method that is typically used, which is in the broad framework of transfer matrix method, is Mikkelstadt-Prall method, which is designed to solve a typical lateral vibration problem. All right, we discussed the transfer matrix method applied to torsional vibrations, but I hope you are also now should be clear that the same problem can be formulated, or same approach and structure can be extended for longitudinal vibrations, that means the axial vibration problem. So, instead of torque and the twist, it would be the axial force and the corresponding axial displacement or deflection in each of the segments. So, that is how f and x will replace t and theta in the Holzer method to generate the same formulation for the longitudinal vibration problem. So, longitudinal vibrations of a propeller shaft or that of the push rod, all of that can be analyzed conveniently using the same approach for which we have discussed as a Holzer method. Okay. So, primarily it was designed for torsional vibration problems, but the same can be easily extended for extended in the sense reformulated in the lateral the longitudinal vibration. But for lateral vibrations, we have to have a relook at the state vectors and the relationship between them, and Mikkelstadt-Prall method was introduced to investigate the lateral vibrations of the continua. Okay. So, the reason for taking Holzer method is that it is simple, the size is only comprising only two state variables. So, therefore, that was a precursor to understanding how the same can be extended for lateral vibration problem. So, we will now look at how the same discretization is implemented in solving a lateral vibration problem. So, we take a continuous system like a beam, in this case shown as you see, into n different segments, quite similar to what we did for the Holzer method. And so, it is discretized into n plus 1 segments, and out of that we focus, let us say, on the ith segment, and then look at how the state vector on the right side is related to the left side of the segment. In the Holzer method, the two state variables, the twist and the twisting moment, were the two state variables which we used. In this case, because the beam is bending in this vertical plane, we will have to check what state variables are required to properly capture the dynamics in the lateral direction. So, we take this ith segment, and as I said, we will relate the state vector on the right side of the ith mass to the left side of this ith mass, and then the state vector on the left side of this ith mass will be related to the state vector on the right side of the previous mass, and that basically constitute one particular segment, in this case shown as the ith segment. That ith segment can have the length denoted as Li, it will have its own properties. So in this case, because it's a flexural vibrations, the property that we are going to look at is the flexural stiffness instead of the torsional stiffness in case of the Hauser method in dealing with torsional vibrations. So in this case, the parameters are going to be a bit different. And as was assumed in the previous case of the torsional vibration, this particular segment is considered massless, and the entire mass of this ith segment is presumed to be concentrated at the end in mi, right. So this mass is the mass of the entire segment concentrated at the extreme right, and as long as your segment is small enough and you discretize the continua in several segments, this assumption is a fair assumption and will not generate too much of an error. So that is something which should be clarified upfront. Now, how do I relate the state vector on the left of the ith mass to the right of the I minus 1th mass? What relations govern between the two? So it's basically the same static equations that we used in the previous case, except that the beam is going to bend in the vertical plane, and that's what is the assumption, that the motion is restricted in only the vertical plane. So it makes sense to look at all your coordinate systems here. So what we assume is that this beam is bending like this in the xz plane, and so a part of this beam is shown here, which is deflecting in the vertical plane. So you can imagine that vertical plane to be this, and in this vertical plane a small segment is shown. Let's look at this particular end of that segment. That segment is having a vertical displacement along positive z direction. So now in this case, the deflection on the rightmost end of that segment is defined as W. Okay, the deflection in z direction. The beam is of course bending in the xz plane. So W is the deflection at that point, theta represents the slope at that point, and then of course there are internal forces, the shear force and bending moment. Shear force being in the downward direction, shear force being along the z direction, that is vertical force. We will follow some sign convention, the material sign convention. So you have Vz as the shear force acting on this face of the segment, and then there is a bending moment acting about the y-axis. So this is the bending moment that acts, and therefore it is shown in this direction. So that is the direction in which the bending moment acts at that particular location. Okay, so these therefore define all the state variables at that location. So the deflection, slope, shear force and bending moment. Whereas in the Hauser method torsional vibration, the only deflection was the twist, so therefore it was only theta, and the corresponding internal force, that is the twisting moment that is set up because of twist. So those were the two state variables. Here there will be deflection, slope and the corresponding shear force and bending moment. So those are the things. Now the sign convention is important. So we follow this sign convention that deflection is positive along the positive direction of z axis. The slope is positive in the counterclockwise direction about y direction, and the shear force bending moment, mind you, they are given these subscripts to distinguish them from the similar forces if the beam bends in the horizontal plane. Okay, so in general this entire method can be extended for the vibrations in both the directions, in both the planes. So therefore upfront one may include these subscripts to not confuse us when we deal with the combined vibration in the horizontal and vertical plane. But we are not going to look into that part as yet, but still as a general convention, we put these subscripts z and y for the shear force and bending moment to appropriately and precisely label them. So my being the bending moment about this y axis, it is considered counterclockwise on the positive phase as the positive values. Okay. And how do we define a positive phase? A positive phase is the one which has outward normal along positive x axis. Now the outward normal of this end phase of the segment, as I mentioned, is in the positive direction of x axis, and therefore we use these conventions to represent the extreme right side of the segment. On the left side, you would have the outward outward normal going in the negative x direction, and in that case the positive shear force will be upward that way, and the bending moment will be in this direction. With these sign conventions and all the state variables defined, let us look at how we arrive at the appropriate matrices which relates the two state vectors. So any beam under bending, we can, as a exaggerated view of it, it can bend in different ways. So this is any arbitrary deflection shape of the beam under bending, although it is shown as cantilever, but it will apply to the beam of different end conditions. It will have deflection, it will have slope all along the length, and as we discussed, we define W to be positive downwards. So this is how the deflection is specified. The slope is specified counterclockwise positive about to the y axis, so therefore theta appears positive that way. Shear force is shown here, Vz, and of course the bending moment being shown there like that. So now with this in place, the various discretized elements, let us say for the ith segment, we show the ith segment here, where the mass of this entire segment is lumped at the extreme right here, as we are representing that as mi, the mass. And on the right side of this ith mass, you have a state vector Si on the right side and Si on the left side. Okay, so this is something very similar to our Holzhausen method, so I need not elaborate too much into this. The state vector on the right of the previous segment's lump mass, that is mi minus 1, will be S right of I minus 1. So our objective, because we are going to discretize our continua into n number of segments, will be to relate the state vector on the right of that segment to the state vector on the right of the previous segment. So once this relationship is established, we will keep on multiplying it subsequently. So this is how we are interested in now establishing the relationship between the various state vectors. Now for this, let us first focus on the massless segment, the ith segment here, and consider various deflections and the corresponding forces which are set up. So this is important that it is massless ith segment. So we are obviously going to look at the static force balance, and for that purpose, let us now represent the deflections on one extreme end of the segment in represent them in terms of the parameters on the left hand side. Okay, so that will establish the relationship between each state variable. Now we will be heavily making use of some assumptions which are existing. You must have learned about all those relationships in your strength of material or solid mechanics course, where given an amount of external force or external moment acting on the beam, what kind of deflections and slopes which are set up. So this these relations you can very easily recall that suppose at one end you fix your beam, and on the other end if you apply it with some moment and shear force, um, or external force, this is how the deflection at the other end will look like. So the deflection is given by this expression and the slope is given by this expression. Okay. uh, so what we are going to do is we will now start writing what is the relationship between these moments and shear forces. Now if you look at the force balance, the shear force on this extreme end, that is on the right of the previous segment, and at this location the shear forces are identical, because between these two ends of the segment there is no other force that exists, right. So the vertical force balance will result into this particular balance equation. So the shear force on the left of the ith segment, that is this shear force, will be equal to this particular shear force, whereas the moment on the left of the ith mass, that is this moment, that moment obviously will be equal to the moment on the other side multiplied by the moment created because of this existing shear force, right. So obviously this equation will be the moment balance equation for that segment, and these two equations are basically the equations arising out of the static force balance. What about the deflections? WIL, the deflection on the right side of the segment. Okay, so WIL actually represents the deflection on just on the left of the ith mass, right. But for the segment it is the right side deflection. Please make a note that this segment is like this. You have this segment, you have a previous I minus 1th mass, and this is ith mass. So there are these two state vectors, right, and the deflection, because this is considered as a point mass, so there is no size associated with it. There is it's a point mass here, lumping the entire mass distributed along the entire segment into a point mass here. So the deflection, vertical deflection Wi on the right side of the ith mass is going to be equal to the deflection on the left of the ith mass, because it's a point mass. The deflection on just on the right and just on the left is going to be the same. There is no slope, there is no deflection across these two state vectors, right. So this is the assumption that we have. So how do I write Wi on the left side equal to, in terms of all the parameters on the left side? See what you have done, you have written Wzi in terms of the value with on the right hand side of the I minus 1th segment, right. So I would like to now write WIL. This will be equal to whatever is the deflection on the right side, that is this deflection I minus 1. Okay. From that I will have to subtract the deflection. It's not a deflection, but it's the this amount of displacement because of the existing slope at this point, isn't it? That much amount of displacement has to be reduced from this deflection, so that I can reach to WIL. Okay. So obviously I will have to subtract from this how much, theta I minus 1 r, that means the slope at this point, multiplied by what, Li. Okay. This is theta into L. Okay. And beyond that there will be this much amount of deflection which will be happening because of the shear force and bending moment. Okay, those forces which are acting on this point, and they will follow this equation, this relationship. Okay. So what do I do? So much of this, and then the moment is counterclockwise like this. So that moment is going to add to that deflect, I mean will get subtracted from the deflection. So minus m y I L, okay, else Li square, because I need to now look at the length which is pertaining to this particular segment, divided by 2 EI. Okay, this is going to be the deflection because of the acting moment at this extreme end, right. So this is what I am basically going to look at. This is actually this deflection. Now I am basically rewriting this expression by using an appropriate m and v values, okay. And then yes, of course, the shear force will try to reduce that deflection. So that is how I will write this as yeah, plus Vz I into L cube by 3 EI. Now in the discretization you can have uh, each segment to have different cross sectional dimensions, right. So if you have a tapered beam, when you discretize you can assume this cross sectional dimensions to be different than this particular segment. So each segment can have its own I value which is going to be different, okay. In fact, theoretically you can also have different material. So if you have a functionally graded materials, if you have a material properties which are changing with the spatial coordinate, then you can in fact theoretically have different I value as well. But this EI can pertain to the flexural rigidity in the ith segment, okay. So you can have subscript II representing that particular segment's property. Now what we are doing is this deflection is being reduced by this deflection will be reduced by the deflection due to moment, and then you will add to that the deflection because of the shear force. So this is how the value of the deflection is going to be written in this way, and you can figure it out that the same way it can be written for the slope as well, okay. So the slope is now the slope at this point, and then that slope will get modified with respect to the slope on the left side of the segment, and using this expression you can add to the slope of at this point based on the moments and shear forces which are acting at this location. So exactly the way we modified the deflection, the slope will also be written like this, okay. You can work this out yourself. Now what is our overall objective for relating the state vector on the left side of the ith mass to the right side of the I minus 1th or the previous segment's mass is to establish this matrix which defines the segment here, okay. So therefore I would like to write all these parameters, okay, on the left side, that is this particular state variables in terms of the state variables on this side. So that is why this state variable and this state variable they are corresponding to the left side of the ith mass. So I need to modify and replace these ones appropriately, so that on the left side I will have all the state variables on the left side of ith mass, and on the right side I will have all the state variables pertaining to the right side of the I minus 1th mass, okay. So there, that part I can do by replacing this variable in terms of the corresponding state variable on the right side of I minus 1th mass. So this is how I do it. Just have a look at it. WIL, which is the deflection at this point, is wi minus 1 r. So this is fine because I am going to get now on the right side all the state variables on the corresponding to this state vector, okay, sr I minus 1. This also is fine because this pertains to the right side of I minus 1. So this is okay. Now this moment will be replaced with this moment, and this one will be replaced with this, okay, will be replaced with this. So I can rewrite this, okay, the right side I can rewrite as m r y I minus 1 plus v z I r, because both the shear forces are identical on either side, Li. So I can use now this mLi equal to this value. So this is how I do it. When I replace it, mry I minus 1 and then you multiply it with this Li square upon 2 Ei, okay, this is minus this, and then I need to add this part, okay. So minus Vz I minus 1 r. Now Li into Li square becomes Li cube divided by 2 Ei. This is with the assumption that the modulus of elasticity is the same throughout the beam or the continua. But as I said, you can keep it different if that is the case. Mostly that will not be the case. You typically use only the same material actually. Okay, so now consider this VZIL, we can replace it with VZ I minus 1 r, okay. So this is getting replaced by this, and then Li cube upon 3 Ei. Now I can write this as you can look at now all the parameters that I have on the right side of this equation have been obtained in terms of the state variables on the corresponding to this point, and I need to simply make little readjustment of these terms. In that I need to club these two, and you can show that this turns out to be Vzi minus 1 r Li cube upon 6 Ei, okay. That is how my displacement relationship is now uniformly brought in the form that the left side of this mass terms are related to all the terms on the right side in terms of the state variables on the right of the previous segment, right, and that's precisely what we want, right. So just like I reformulated this uniformly, bringing all the right hand side terms corresponding to the state vector on the left of the segment, I can similarly do it for the slope here, which I did for the deflection here, okay. So that part is left to you to figure that out, but it's a straightforward activity. And then I can now club all of these, or I can represent all these 4 equations into a matrix form, which relates all the state variables on the left of the ith mass to the state variables on the right of the I minus 1th mass, okay. So look at this, all these state variables, W, the deflection, the theta, the shear force, the bending moment on the left of ith mass are forming one state vector, and the similar parameters, similar variables are on the right side of this equation with a matrix establishing the relationship between them. Now you would scratch your heads as to this looks little odd as to why you have taken this deflection negative, right? But that is mainly for some mathematical simplicity, mathematical adjustment, in the sense that by doing that all these terms in the matrix becomes all positive, as you can see, right, and doesn't change anything actually. So there is absolutely nothing wrong in doing that, and you can see that the moment you have this written as negative deflections, you all the same equations you get by expanding this matrix. So there is absolutely nothing problematic there. It's just a convenience sake. Okay, that's how you get the relationship between one state vector here with respect to the state vector here, and this relationship is for that massless segment, and therefore the matrix relating these two state vectors is called as a field matrix, quite similar to your Hauser method, where we use the similar way of static equilibrium and force balance to get the relationship, right. So this is the field matrix that you get, and now for, as I said, getting the relationship between this and this, we need to establish this relationship across the mass element, right. So for that, what do? You consider this mass segment or a point mass, which is the lumped mass of the entire segment at the extreme right side, and then all these state vectors are again similar to what we have discussed earlier. Now what you should understand, that the deflection on the right side of this mass and on the left side of this mass, the mass being point mass, is going to be same. So the W is same, and across that element there is no change in the slope, so the slopes are also same, right. Can we say about the moment? Because it's a point mass, it doesn't have mass moment of inertia, okay, so the moments are going to balance, okay, or the moments are going to be identical on the left side. On the right side there is no difference in the two moments, so the moments are same, okay. What about the shear force? The force on the left side is this VZIL, and on the right side the shear force is VZIR, okay. But because this mass has its inertia and it is vibrating, it will have, I mean, we will have to look at the force balance in the vertical direction. If you take the force balance for this dynamic motion, then mass times the acceleration will have to be equal to the net force, okay. The net force is going to be the difference between VZIR and VZIL, okay. So the relationship turns out to be this, mass times acceleration is the net force acting in the direction of acceleration. This is W and W double dot, that's how you write it, okay. And then we assume we are trying to do this for evaluating the eigenvalues, right. So when we are evaluating eigenvalues, our assumed response will be what? A harmonic solution, okay, which means that it is going to be minus mi omega square Wi equal to the same force difference, okay. So although the deflections are same, the slopes are same across the mass element, across the point mass, the moments are identical, they balance each other out. The shear force difference is the fictitious force, the inertia force, okay. But applying the Newton's second law, we can get that relationship. The difference in the shear force turns out to be minus mi omega square Wi, right. And using these equations that I just discussed, that Wi on the right side, Wi on the right side is equal to Wi on the left side, theta I on the right side is equal to theta I on the left side, my on the right side is equal to my on the left side, and this one, okay. You can now write the relation in the matrix form. Yes, of course, minus WIR is equal to minus WIL, theta is equal to theta, and therefore all the diagonal elements will appear. So here also you can see that I can rewrite this as V Z I R equal to V Z I L minus or I will write this as M I omega square into minus W I, right? And because this is minus W I, this is what equation that you get. The last row is going to be what we have got here. That is how this relationship establishes the state vector on the left hand side of the ith mass with the state vector on the right side of the ith mass, and that mass is a point mass. We call this as a point matrix, okay. And this matrix relationship now can give us the overall relationship across the entire segment. So this is how we got started with. We established this field matrix, and then we also established this point matrix, right. So this is how the state vectors are related, and now it is quite easy that I can replace this particular state vector using this relationship, so that I get the relationship between the two state vectors. So where of course these are the two equations that we recall from the previous slides, and now I can replace this SIL which is this state vector here in terms of this state vector, and then that's how you get Pi into Fi multiplied by this state vector. In the context of both Holzer method and transfer matrix method, Mikkelstadt-Prall method, it is extremely important to understand that the sequence of these matrices are important. You cannot flip the two matrices. It's quite clear from the state vector relationship, right? So they should come in the same sequence. First the point mass followed by the field matrix, point matrix followed by the field matrix. And now we club these two matrices just the way we did it for the Holzer method. Now we call the transfer matrix as a product of the point and the field matrix, and once you do that, we can now relate all the state variables on the right side of the ith segment to the right side of the I minus 1th segment through a matrix called as a transfer matrix, that is Ti, okay. And the transfer matrix, after you do this multiplication, this multiplied by this would give you the product gives you this matrix, quite straightforward, okay. Now again, as we discussed, this is just one segment. Our job is to formulate the entire problem of the beam, so we will have to now keep on multiplying each transfer matrices to generate an overall transfer matrix, right. So that's what we are going to do. What you can notice that because the state variables are 4 in this case, slope, deflection, shear force, bending moment, the size of the transfer matrix is 4 in lieu of 2 in case of the Holzer method. So what you do for considering the entire continuum, because S1 is related to S0. Now here there is nothing like 0th element, but we take this state vector to be S0, and now what happens is that a massless segment multiplied by the mass, which is T1, relates the state vector just on the right side of the first segment to the S0 segment or S0 state vector. So S0 state vector need not necessarily have, I mean there is no need to write R here. You can just write S0 as the state vector, which is the extreme state vector on the left side. They get related through this transfer matrix T1, and where Ti or any ith segments transfer matrix is given this. So S2 will also get related to S1. So similarly, this state vector is related to this state vector through the transfer matrix T2, and so on. So you just keep replacing this particular state vector from this relation, so you get T2 into T1 and so on. So you can therefore now relate the extreme right side state vector with the extreme left side state vector through all these transform matrices. In a way, sometimes depending upon the situation, you may only consider the field matrix for this, and sometimes you may lump the mass of this segment into this point masses. All kinds of minor updation can be done, depending upon what you are investigating, but a generic approach is to write the relationship between the extreme two state vectors like this. Okay. The product of all of these transfer matrices can be now written as an overall transfer matrix, quite similar to what we did for the Holzer method, and therefore the relationship between all the state variables on the extreme right to the extreme left now happens to be through the overall transfer matrix, having all the 4 by 4 matrix elements defined as Uij. And the way we did it for the previous case of the Holzer method, now the job will be to set up a frequency equation, right? This is the process that we get irrespective of whether the beam is a cantilever or a simply supported or a fixed fix. We never put any restriction on this because the deflection and slopes and all the parameters, they pertain to a generic deflected beam. Now for natural frequency and mode shapes, let's apply appropriate boundary conditions. Now let's take one example of a simply supported beam. Now for simply supported beam, let's say this hinged at one end, okay, and supported simply at the other side as well. What are the boundary conditions for a simply supported beam? Now you have 4 state variables here, right? Deflection, slope, bending moment and shear force. So at the ends, what are the boundary conditions? The deflection is obviously 0, right? So W at both 0 as well as n plus 1 is going to be 0. The deflection is going to be 0. Is the slope 0 for a simply supported beam? No, the beam can deflect at these supported ends. Deflect in the sense it will have non-zero slope, okay. It may not have a deflection at that point, but it can have a non-zero slope. So therefore we cannot write anything related to theta, the slope, okay. And because it is supported there will be shear force generated at the ends, right? The shear force cannot also be set equal to 0. So what you know very well is that my at 0 and n plus 1 both is 0 for the simply supported end conditions. So that is how we have, and therefore when you substitute for W equal to 0 and my equal to 0 at both n plus 1 and 0, then this is what a matrix equation gets modified. Now you can filter out the rows having 0, rows having these zeros. So obviously by doing that you can show that if I take only the first and third row, this is what I will finally get as the reduced matrix equation if I consider only the first and the third row. And you know very easily that if this equation is to be satisfied, then the determinant of this matrix should be 0, which actually means that u12 u34 minus u32 u14 equal to 0. That product, that expression has to be 0 for this to get satisfied at all times. Clear? So what will be our objective now is to assume some omega value, okay. Assuming that omega value, you know that your transfer matrix gets completely defined for that particular assumed omega value, because the length is known, the flexural rigidity of each of the segment is known, masses are known, so you can completely numerically evaluate Ti. In fact, at all segments. You multiply all t's together to generate the overall transfer matrix, and then only select those number of elements to and evaluate this particular relation or equation. So find out whether this equation is equal to 0 numerically. Okay, and if this is equal to 0, then that becomes your natural frequency. If it is not, then you iterate, change the omega value, increase it in steps, and iteratively you will have to keep on evaluating the value of this particular expression, and uh, you might get a sign change across one step change in the value of omega. Okay, so you are changing the value of omega, and the way we did it in the previous case of the Holzer method, instead of one single element, now it is going to be this expression that has to be checked. So you will plot this expression as a function of omega, and then find out at what omega the value of this expression is 0. That can be obtained by tracking the sign change across the step change in the omega value. Once that is done, that basically is your value of the natural frequency. You keep on doing this, later on at certain other higher value of omega, you will find the next sign change that becomes your second natural frequency, and so on. Okay, that is how you do it, and that's what we learned in the previous Holzer method, the root searching method. For cantilever beam, what would be the difference in this case? The expression would obviously change, the characteristic equation, sort of a frequency equation in fact. So if you have a cantilever beam, the boundary conditions at the two ends will not be identical. At left hand end, what is the boundary condition for a cantilever beam? Deflection 0 and slope is 0, and on the extreme right, which is a free end, okay, in that case it is going to be shear force 0 and bending moment 0. So that is how at the nth location or n plus 1th location, these are the boundary condition, and you can follow the same process as we discussed here. You will find out that you get a new frequency equation, and the same approach then gets followed. Okay, now what if you have a beam? You remember that we had a cantilever beam with a shroud, a turbine blade with a shroud here. Shroud in the sense there is a bigger mass at the tip, and those are there for specific purposes. We discussed that as well, but let's now look at, understand as to what do you do when the beam is suddenly have a additional mass which is put on. It's not continuously constant dimension, and the mass distribution is not gradually changing. It suddenly you will have a lumping of the mass at the tip. What do you do in such cases? Again, this entire process is an approximation anyways, right? So you will be discretizing it, and I can have the last end element to be like this. If this distribution is not regular and it is small in size, but there is enough additional mass there, I can lump the mass of this entire segment into the mass of this particular segment here. Okay, so the transfer matrix corresponding to the end segment here will have in your point mass, the mass which is located here, mi into omega square. So this mi will be not only the mass of this segment, but I can use this mass, the tip mass, to get added to it. Okay, if you can formulate and understand the geometry here properly, and this mass is distributed reasonably in a longer length, then you can also assume this to be a separate segment. Okay, but then that segment's flexural properties will have to be properly evaluated and used as the last segment. Okay, and then its own mass distribution can be lumped at the end, and that is how you need to make use of these. So there are, you can then look at what can be, how you can include the root flexibility of the cantilever at its root, but those are all, you know, add-ons or additional things that you need to learn a little bit more, but at least the basic philosophy of this transform matrix method should be clear to you. These complexities can be you know, added on once you are comfortable analyzing the standard problems at least. So if your properties like the cross sectional dimensions are continuously changing, as I said, that is very typical of a cantilever beam, that is very typical of the blades on the gas and steam turbines. You can discretize this into several segments, and each segment's cross sectional properties can be assumed constant in the segment, right? Now there would be obviously inaccuracies, because depending upon how wide the segment is, your properties are going to be an approximate estimate of the entire segment, because you are averaging it out, right? So therefore, what is the effect of the discretization? Okay, what is the effect of discretization? I mean that you plot, you first discretize this tapered beam, okay, a turbine blade, into, let us say, 10 number of segments. So you will have these 10 segments here, and with 10 segments, so I will write this as n, which is representing number of segments, and you evaluate all the natural frequencies, you know, m omega I. So you can list down, or you can plot on this, let us say, first 5 natural frequencies, which you will find or evaluate based on the discretization into 10 number of segments. So you will, from analyzing this, you will get omega 1, omega 2 and omega 5, right? Let us say, to start with, let us say we are interested in the first 5 modes. And then what happens is, when you discretize this into 10 number of segments, you get omega, let us say you get omega 1 here, and when you discretize into 20 number of segments, you get some other, I mean, you get the value of the same omega 1 here, and so on. So what happens is, after a certain number of discretization, there would be no change in the natural frequency value, okay. Similarly, omega 5, if you plot with less number of segments, you are bound to get some error, okay, you are bound to get error, but after some time, after some number of discretization, the difference in the value of the 5th natural frequency, basically the difference is not much at all. You can set some tolerance value that I will accept the discretization if the improvement in the accuracy of improvement in the value of the natural frequency corresponding to the previous coarser discretization is not much, beyond not more than 1% or so. So that is user settable threshold, and then based on that, then you can arrive at an optimized value of the number of discretization or number of segments that this particular continua can be discretized, okay. Larger discretization means more number of segments, but then your matrix multiplication iterations will increase, right? So that is the only issue, but once the overall transform matrix is obtained, the root searching process is going to be still the same. Good thing about this method is that there is no matrix inversion, only matrix multiplication, and so standard commercial softwares can be conveniently used for matrix multiplication and getting the eigenvalue analysis made. So this is called as investigating the convergence of the natural frequency with the discretization, with the number of segments. So how many number of segments is good enough for me is based on how many frequencies are going to be tracked, Now, how many frequencies? Again, you all know that you will get one natural frequency, second resonance, third resonance, fourth, fifth, and so on. But if you are not going to operate at this speed of operation, if your operating speed range is limited within couple of natural frequencies, there is no point in evaluating accurately the 10th mode and the 15th mode and 20th mode, right? So therefore, in general, it suffices to ensure that the first 5 natural frequencies should be accurate enough. That number is also not sacrosanct, just approximate. So this convergence study, finding out how the natural frequency converges with the number of segments, helps you to have confidence that your discretization into those many number of segments is going to give you reasonably accurate results. Okay, that these are all the pitfalls of every numerical approach, not which is not the case when you used the more accurate analysis based on the continuous systems, where the values that you get are actually most, I mean, they are the accurate and they are the correct values. But we cannot have modeling of every system, vibratory system, as a continuous system, and therefore these approximations are anyway required. Yeah, after this, once you have obtained for this lateral vibration problem all the eigenvalues, all the natural frequencies, how do I find the mode shapes? Now that part is something which is quite similar to our method which we discussed in case of the Holzer method. No, you first find out, you assume the deflection. For example, in the cantilever beam, in the case of the cantilever beam, you discretize this into several segments, and the state vector here was w, theta, m and v, and I can now simply state that the deflection at the free end is equal to 1 unit. Okay, so I do not know what is the theta value, and m and v, they are anyway zeros. Okay, so you starting with this particular state vector, okay, I can keep going backwards exactly the way we have done it for the Holzer method. So you assume that the deflection at the free end is equal to 1 unit. With respect to that 1 unit, how much is the deflection at each of the each of the segments? This is something which you can always calculate going back exactly the way we have done it in the Holzer method case, right? So that part I am not going to repeat, it's quite straightforward, and you can again go back to Holzer method and find out how I have done that, right? Theta will be replaced in terms of the parameters on the extreme left, right? So those are the things that you can refer and do it for the Mikkelstadt-Prall method as well. So that's how this transfer matrix method is all about, and gives you a glimpse of how we can use this method for evaluating the main vibration characteristic. You can of course use this method for post vibration response also, which is something which you can read on your own. Currently we are going to restrict ourselves in just the eigenvalue analysis of these problems. The advantage here, as I said, no inversion of matrix required, and irrespective of the number of segments, the matrix size still remains 4 cross 4, right? So the matrix size is something which is the most important plus in the transfer matrix method. If you take a finite element method kind of a setting, then the size of the matrices are going to be proportion to the number of discretized segments that you will. So the size becomes very big for large discretizations, and for very large and complex shapes, number of segments required are large, and therefore the size of the system matrices is going to be very high, and that is not the case here. So this is the reason why this has been very popular method for solving vibration problems. But of course, finite element method has picked up and it has its own merits. But you can use this, write your own simple codes to get a reasonable accurate results using this method as well. The summary of this lecture: we discussed the transfer matrix method, commonly called as the Michelstadt-Prall method, for investigating lateral vibration of beams, and we explored how different boundary conditions of a beam are implemented to get the right eigenvalues and eigenvectors. These are the review questions that you can attempt based on the lecture today. These are the answers.